Good morning students. In previous lecture we have learned about Laplace transformation and properties of Laplace transform. Today we are going to know about derivative of Laplace transform. Derivative of Laplace transform. Derivative of Laplace transform. In derivative of Laplace transform, we have to prove f dash of s or df by ds is equal to L of minus t into f of t. Okay, in derivative of Laplace transform, what we have to prove? F dash of s is equal to df by ds is equal to L of minus t into f of t. And in general, how can you represent this derivative of Laplace transform? L of t power n into f of t is equal to minus 1 whole power n fn of s is equal to minus 1 whole power n dn f of s by ds power n. So in derivative of Laplace transform, mainly we have to prove this. In general, how can we represent the derivative of Laplace transform? L of t power n f of t is equal to, okay, minus 1 whole power n into d power n into f of s by ds power n. Now coming to proof, we know f of s, small f of s. Here small f of s represents the Laplace transform. Okay. Or L of f of t also represents the Laplace transform. Is equal to, what is the formula? Integral 0 to infinity e power minus st f of t into dt. It is well known to you. Okay. How can you represent Laplace transform? F of is equal to integral 0 to infinity e power minus st into f of t into dt. Now, differentiating this equation, okay, we are going to differentiate this equation with respect to s. Differentiating above equation with respect to s. With respect to s. So, what you will get more? Differentiation of f of s is nothing but f dash of s is equal to. Now, or you can represent it as df by ds is equal to integral 0 to infinity with respect to s. No. So, what you will get here? Minus t into e power minus st f of t into dt. So, differentiating this whole term, you will get integral 0 to infinity minus t into e power minus st into f of t into dt. Now, this can be written as, now you bring this e power minus st and include minus t towards the f of t. So, this term can also be written as integral 0 to infinity e power minus st, okay, minus t into f of t into dt. Now, this whole term can be written as, you know, integral 0 to infinity e power minus st f of t dt is nothing but L of f of t. So, what is the remaining term here? Minus t. Okay, so minus t into f of t is, we got the required RHS. So, what we have considered? F of s we have considered. Actually, this differentiation we have proved f of s or df by ds is equal to L of minus t into f of t. Now, if you carry differentiation for n times, then we are going to prove, okay, then we are going to prove Fn of s. That means we are for one time we are applying differentiation. So f dash one time. So if you carry differentiation for n times, so what you will get? Fn of s is equal to d power n by ds power n is equal to L of minus 1 whole power n t power n into f of t, or you can write it as minus t whole power n into f of t, or you can write it as minus 1 whole power n into L of t power n into f of t. So hence we have proved the derivative of Laplace transform. Next we are going to know about Laplace transform of derivative. Okay, Laplace transform of derivative. Next we are going to know about Laplace transform of a derivative. Laplace transform of a derivative. Laplace transform of a derivative. Now in this we have to prove L of df of t by dt is equal to L into S into L into f of t minus f of 0, that is equal to S f of s minus f of 0. So this we have to prove in the Laplace transform of a derivative. Now to prove this, first consider LHS. Coming to proof, consider LHS. What is LHS? L of df of t by dt. We have considered LHS. Now you know that only L of f of t you know. What is L of f of t? 0 to integral 0 to infinity e power minus st f of t into dt. Only we have to apply the differentiation. So we can write this differentiation of Laplace transform of derivative as integral 0 to infinity e power minus st df of t by dt into dt. Okay, we can express this as integral 0 to infinity e power minus st into df of t by dt into dt. Now integrating by parts. Okay, so in integral uv method we are going to apply. So integral uv formula is u integral v minus integral differentiation of u into integral v. So same formula we are going to apply for this. Here u is nothing but e power minus st, v is nothing but df of t by dt. So by applying this integration by parts formula, so what you will get? U in the sense e power, so this term remain like that only. So u in the sense e power minus st integral v. Here integral v is nothing but 0 to infinity df of t by dt into dt minus integral differentiation of this. So minus integral 0 to infinity differentiation of u. Differentiation of u is nothing but minus t, sorry, minus s with respect to t no. So if you do with respect to t, what you will get here? Minus s e power minus st into dt integral 0 to infinity df of t by dt into dt. So according to this formula I have expanded this. Now we will get here integration, differentiation gets cancelled and applying the limits for f of t. So what will get here? E power minus st into f of t. Applying the limits 0 to infinity. Minus to minus it becomes plus. Yes. Integral 0 to infinity e power minus st. Okay, here also integration differentiation gets cancelled. Okay, f of t dt will be remained. Now we are going to apply the limits. So upper limit minus lower limit. So e power, wherever t is there, you have to apply the infinity. So e power minus s infinity into f of infinity minus lower limit no. So e power minus s of 0 into f of 0. So we have applied the limits. Plus. So here what you will get? Yes, integral 0 to infinity e power minus st f of t into dt. Okay, here minus s of infinity, it's undefined. Okay, so what you will get? It becomes 0 and its value is 0 minus e power minus s into 0, 0 only. E power minus 0 is 1 and f of 0. You will get plus, yes, integral 0 to infinity e power minus st f of t into dt. Okay, f of t into dt. Now this here 0 minus f of 0 is nothing but minus f of 0 plus s. Here integral 0 to infinity e power minus st f of t into dt is nothing but L of f of t. Okay, or you can write it as minus f of 0 plus s. L of f of t can be written as in lower case f of s. Okay, and hence we can write it as s into f of s minus f of 0. Okay, hence we have proved the this Laplace transform of derivative. Okay, we have considered the LHS. Next, Laplace transform of periodic function. Laplace transform of periodic function. In Laplace transform of periodic function, we have to prove L of f of t is equal to integral 0 to t e power minus st f of t into dt by 1 minus e power minus st. So in Laplace transform of periodic function, what we have to prove? We have to prove L of f of t is equal to integral 0 to t e power minus st into f of t by f of t into dt by 1 minus e power minus st. So to prove this, first consider LHS. Here LHS is nothing but L of f of t. L of f of t. So how can you represent L of f of t? Integral 0 to infinity e power minus st f of t into dt. It is well known to us. Now we have to express this limit in terms of periodic function. In the sense 0 to t, t to 2t, 2t to 3t, 3t, 3t to 4t and so on. That means we have to express the integral part in terms of periodic function. So I am splitting. We are going to split this 0 to infinity in terms of periodic function. That is equal to this LHS remain like that only. Now we are going to split the integrals. First 0 to t. E power minus st f of t into dt plus integral t to 2t e power minus st f of t into dt plus integral 2t to 3t e power minus st f of t into dt and so on. Now substituting, small t is equal to u plus capital T. Output, small t is equal to u plus capital T. In the second integral in the sense here, and in second integral, and t is equal to u plus 2t in third integral and so on and so on. So what you will get? So what you will get here? Integral 0 to t e power minus st f of t into dt. There is no change in the first term. Only we are bringing the changes in the second term and third term. Now plus integral 0 to t 0 to t e power minus s of u plus t is nothing but here in place of t, u plus t you have to substitute. So u plus t into f of u plus t into du, because we are writing the function in terms of u, plus integral 0 to t. Why we have considered the same integral? In order to make it as a periodic function. Periodic function in the sense the limits will be same for all the integral terms. So here 0 to t e power minus s. In the third term, what we have to keep in place of t? U plus 2t into f of u plus 2t into du and so on. Now you write down the first term like that only. Integral 0 to t e power minus st f of t into dt plus from the second term you bring e power, that means you multiply minus su minus su minus st you will get. So I am bringing e power minus st out of the integral. So what you will get? 0 to t e power minus su is remained f of u du. Next, I will tell why we have considered f of u plus t as f of u. We will consider in the since part. Now in this also you bring here e power minus 2st out of the integral, then the remaining terms are 0 to t e power minus su, okay, f of u into du. Since f of u is equal to f of u plus t is equal to f of u plus 2t, that is equal to f of u plus 3t and so on. So wherever f of u plus t or f of u plus 2t and so on, what you have to keep? F of u. So in this place we have substituted the f of u. Now we are going to write a function in terms of u as in terms of t. So what you will get here? integral 0 to t e power minus st f of t into dt. This is the first term like that only. So other terms we are writing in place of f of u is there. Just we are writing the function in terms of t. So e power minus st integral 0 to t e power minus st f of t into dt plus e power minus 2 st integral 0 to t e power minus st f of t into dt, and so on we got. Now from all the terms you bring integral 0 to t e power minus st f of t into dt as common. So if you take that term as common, what you will get? 1 plus, okay, in this term 1. Next term my e power minus st. The second term, in the third term e power minus 2st you will get, and so on. What is the common term we have taken? 0 to t e power minus st f of t into dt more. Now we can write this as, since we know 1 plus a square plus a cube plus and so on is equal to 1 by 1 minus a. Okay. So similarly the above term can be written as 1 by 1 minus, here a is nothing but e power minus st. E power minus st. Okay, so this whole can be written as in the form of 1 by a. 1 by 1, a is nothing but, you compare, e power minus st. Integral 0 to t e power minus st f of t into dt. Or you can write it as integral 0 to t e power minus st f of t into dt by, okay, by 1 minus e power minus st. So what we have to Laplace transformation, that is L of f of t we have considered, and we have proved it will be equal to 0 to t e power minus st f of t into dt by 1 minus e power minus st. Hence we have proved the Laplace transform of periodic function. Next we are going to know about inverse Laplace transforms. Okay, next concept is inverse Laplace transforms. You know how to represent the Laplace transform. How can you represent Laplace transform? L of f of t is equal to, in lower case, f of s. Now you want to find the inverse Laplace transform, inverse of Laplace transform. That means inverse of Laplace transformation operator. So how you will get, if you send to the RHS, you will get the inverse of it. So f of t is equal to L inverse of f of s. So the question is, the concept is inverse Laplace transform, no. So therefore L dash of f of, L to the power of minus 1 into f of s is equal to f of t. That means inverse Laplace transform is it's denoted by L inverse of f of s is equal to f of t. Here L inverse is called inverse Laplace transform operator. So in Laplace transformation, L is nothing but Laplace transformation operator. So here L inverse, L to the power of minus 1 is nothing but inverse Laplace transform operator. Inverse Laplace transform operator. Transform operator. Now we are going to solve different properties of inverse Laplace transform similar to the Laplace transformation. So in properties of inverse Laplace transform, we are having the linearity property, okay, then change of scale property, first translation, second translation. That means 4 properties are there. Okay, like similar to Laplace transformation. So first we are going to know the properties of inverse Laplace transform. Inverse Laplace transform. You know how to represent the inverse Laplace transform. How can you denote L inverse into f of s is equal to f of t. Now we are going to know the properties of inverse Laplace transform. So the first property is linearity property. The properties are very simple now. Okay, linearity property. In linearity property, we have to prove L inverse of. We have to prove L inverse of C1 f1 of s plus C2 f2 of s is equal to C1 L inverse of f1 of s plus C2 L inverse of f2 of s. So, in linearity property, what we have to prove? L inverse of C1 f1 of s plus C2 f2 of s is equal to C1 L inverse of f1 of s plus C2 L inverse of f2 of s. So, to prove this, first consider the LHS. So, what is LHS? First, you consider like similar to Laplace transformation, then we will do inverse for that. First, consider in term of L. L of C1 f1 of t plus C2 f2 of t. f2 of t is equal to, you bring C1 outside. So, how can you write? L C1 f1 of t plus L C2 f2 of t. Now taking inverse Laplace transform, how can you write? This can be written as C1. That means I am going to send this inverse to that side. Now, first we have considered, according to the linearity property of Laplace transform, we have considered this one, L of C1 f1 of t plus C2 f2 of t. So, this we have considered according to the Laplace transform linearity property. Then we brought C1 out of bracket, then we have written. Now you can write this term as L C1 f1 of t is nothing but f1 of s plus next here L of f1 of t is nothing but C1 f1 of s plus here L of f2 of t can be written as f2 of s. So C2 f2 of s. Now send this L to that side. That means taking inverse Laplace transform. What you will get here? That means here L is there. If you send that side, then you will get the inverse Laplace transform. So what is remaining in the LHS? C1 okay, f1 of t plus C2 f2 of t is equal to, I am sending L to the RHS side. So what you will get? It becomes L inverse of C1 L inverse of C1 f1 of s plus C2 f2 of s. Now we can write it as, now this L inverse is for this term as well as this term. Now this can be written as C1 L inverse of F1 of S plus C2 L inverse of F2 of S. Okay, so hence we have proved the linearity property of inverse Laplace transform. So we got RHS, isn't it? Yes. So therefore, what is the considered thing? L inverse of C1 F1 of S plus C2 F2 of S is equal to C1 L inverse of F1 of S plus C2 L inverse of F2 of S. Okay, so hence we have proved the linearity property of inverse Laplace transform. Next we are going to know about change of scale property. Next one is change of scale property. Today we will continue with the change of scale property. Thank you.